Welcome back, everyone. In this video, we will learn how to calculate heat. Here we have three equations that we can find on table T to calculate heat. We also have table B that gives us the physical constants of water. Let's get started. So, when do we use these formulas? Let's start off with the first one. Q equals MCAT. Q equals MCAT, you're going to use that equation when there's a change in temperature. Delta T is the final temperature minus the initial temperature. So capital T stands for temperature. Delta T equals final temperature minus initial temperature. This is the formula that we use when there's a change in temperature. So, when do we know when to use this formula? Let's say the problem gives you an initial temperature but doesn't give you a final temperature, or vice versa. And they're asking you to find either the final or the initial temperature. That would be an indication that you're using this formula. Or let's say the question doesn't give you an initial or final formula, but it tells you that the temperature increased by so and so Kelvin. It could either say temperature increased or decreased by this much. That is telling you right then and there the change in temperature. Okay, so this equation we use to calculate heat when there is a change in temperature. Now the next two are when there isn't a change in temperature. So when do we use Q equals MHF? HF stands for heat of fusion. We use this formula when something is either freezing or melting. So in a problem, how are we going to know when to use this formula? Keywords here are if they say something is melting or something is freezing, or they can say something is changing from a solid to a liquid, which is the same as melt, or something is changing from a liquid to a solid, which is the same as freeze. So let's take a look at this example here. What is the amount of heat required to completely melt a 200-gram sample of H2O at STP? Okay, it says I need to calculate heat. And it says that this substance is melting. What is the substance? This is water. And there's 200 grams of water. And it says that it's at STP. So let me think about this and see, okay, is there a change in temperature? Because if there's a change in temperature, then that means that I need to use Q equals MCAT. But they mention STP to throw you off. This is at a temperature, but they don't mention anything about change of temperature. They say it's at this temperature, nothing about it changed or it increased or it decreased, nothing. So that's extra information, and that's why I crossed it out. So we are using this equation for this example. The keyword here is melt. So how would we set this up? Well, Q stands for heat, so that's what we're going to find. That's our X. So Q is our X. The M is the grams, or the mass, and they tell us we have 200 grams. And then they say we have H2O as the substance. And they don't give us the heat of the heat of fusion of water. They don't give us the HF of water. And the reason they do this is because on table B, you are given the physical constants for water. And heat of fusion for water is 334. So that would be plugged in here. All right. Let's keep going. Let's go to heat of vaporization. So HV stands for heat of vaporization. We use this formula when something is either vaporizing or condensing. So keywords that we'll see in a problem to indicate that we're going to use this equation. If they say something is boiling or vaporizing or changing from a liquid to a gas or a liquid to a vapor, that is indicating that something's boiling. So you're going to use this equation. They can also mention condensation. If something is changing from a gas to a liquid or a vapor to a liquid. When either one of these is happening, we're going to use heat of vaporization formula. So let's look at the second example. It says, show a numerical setup for calculating the quantity of heat in joules required to completely vaporize 102.3 grams of water at 100 degrees Celsius and 1 atm. Once again, first thing, is the temperature changing? If it's not, then we're stuck with the other two equations. Here, they mention a temperature, and they don't mention that it changed, that it increased, that it decreased, that this is the initial or the final, nothing. So, I know I'm not using Q equals MCAT. I can rule that equation out. And pressure also is extra information. Nothing to do with calculating heat in this case. So, I'm going to use this keyword, vaporize, and I know I'm using this equation, heat of vaporization. So how would this look like? For this, I know that the X is Q because they're asking me to calculate heat. Q stands for heat, and the unit for heat is joules. So I'm going to set this up here. Q is my X. Q equals M. In this case, M is 102.3 grams. And then we have HV, and they tell us the substance is water. So they don't give us HV. And the reason they don't do that is because we have it here. Heat of vaporization is 2,260. So I'm going to put this 2,260. Okay, now let's move on to what we were seeing before, which was the heating curve and the cooling curve in the last video. The heating curve, I have it here of when we would use these equations. So Q equals MCAT is when the temperature is changing. So when the temperature is increasing from A to B, that is temperature changing. So we would use Q equals MCAT on this line. Same goes to all of the slopes. So we have it when the substance is in one phase, we're using Q equals MCAT. When the substance is going through a phase change, so for instance, this would be melting, and this would be boiling. When it's going through a phase change, the temperature is not changing, so we're going to use for BC, for when it's melting, we're going to use the heat of fusion equation. When it's boiling, we're going to use the heat of vaporization equation. Now for the cooling curve, the same thing is applying. So on the slopes, when the temperature is changing, In this case, now the temperature is dropping, is going down. That means that we're going to use Q equals MCAT. So the same thing that we talked about in the heating curve, the slopes, Q equals MCAT. And during the phase changes, you're going to use either the heat of vaporization or heat of fusion. For instance, this right here is a gas, this is a liquid, and this is a solid. So from a gas to a liquid, we're going to use the heat of vaporization equation, which is used for either boiling or condensation. And then we have from D to E, we have freezing. Heat of fusion is used when something is either freezing or melting. All right, let's move on to what we just reviewed. So heating and the cooling curve side by side, you can see that on the slopes, you use Q equals MCAT. When there's a phase change, you use either heat of vaporization or heat of fusion. What depends on is for heat of fusion, you use it when something is melting or something is freezing. Heat of vaporization, use it when it's something's condensing or if something is vaporizing. Let's go to the first question. What is the amount of heat required to melt 43 grams of solid magnesium oxide at its melting point? The heat of fusion is 1.9 times 10 to the third power joules per gram. All right, so what equation are we going to use here? Let's take a look at it. It says, what is the amount of heat? So I'm calculating Q, but there's 3 equations that calculate Q. So let's roll out the first one. If there's a change in temperature, I'm using Q equals MCAT. If there isn't, I'm not using this. Let's see, in this question, we weren't given any temperature, so we're going to cross this one out. And then the key word here is melt. So melt, when something is melting, I'm using the heat of fusion equation. So this is the equation that I'm using. We can't use heat of vaporization because it's not either condensing or boiling. So let's set it up. Q equals MHF. Another thing they mentioned is that they gave us the heat of fusion. So this is HF here. And they also gave us the grams. So they gave us Q equals 43 grams. And they gave us the heat of fusion, which is 1.9 times 10 to the third joules per gram. By the way, 1.9 times 10 to the third is just moving the decimal place 3 times to the right. That's the third power that that's telling you to move it to the right. 1, 2, 3. So 1.9 times 10 to the third power is 1,900. That's that number. 1,900. Okay, now if you put this on your calculator, you're going to get an answer of 81,700 joules. Or let's say that the question is asking you to calculate the heat in kilojoules, which is sometimes what they will do. They will ask you to calculate the heat in kilojoules. Your answer is in joules. In order to go from joules to kilojoules, there's 2 ways. You can either move the decimal 3 places to the left, or divide this by 1,000. So 81,700. There's no decimal. When there's no decimal, you're going to start at the very end of the number, and you're going to go 3 places to the left. So 81,700 joules is equal to 81 point, because that's where it stopped, 7 kilojoules. Okay. I mentioned this because sometimes they do make you do an extra step at the end and ask you in kilojoules instead of joules. So here you are, how to convert that. Either 3 decimal places to the left, or you divide it by 1,000, whichever one works for you. So we're done with this problem. Let's go to question number 2. It says a 36-gram sample of water has an initial temperature of 22 degrees Celsius. After the sample absorbs 1,200 joules of heat, the final temperature of the sample is... All right. Once again, we need to determine which of these equations we are going to use. This right here mentions initial temperature is 22. And they want me to find the final temperature. So there can only be one equation that I use here. It's the first one, Q equals mcat, because the other two do not mention temperature. The only one that involves temperature is when there's a change in temperature, and that would be the first one. So I'm going to write it down here. Q equals mc delta T. I'm also going to write this out because I want us to know what delta T is. So we are all on the same page. So delta T is final temperature minus initial temperature. All right. So let's start plugging numbers in. Here we have that the mass is 36 grams. We know that the initial temperature, so Ti, is 22. And then we know that the heat, because they gave us joules, this is 1,200. So I'm going to start plugging it in. Now, I do not have C, but they told me that the substance we're talking about is water. So they don't need to give me C. C is on table B because they gave me the physical constants of water. The physical constants of water are here. So the specific heat capacity of water, which is C, is 4.18. So this is C right here. They give you C, but they don't give you it in the question. They expect you to find it on the reference table. So C is 4.18 joules per gram times Kelvin. All right. Let's see what else we have to do. And then this is the final temperature minus initial. We don't have the final temperature, so we're going to leave an X there, and we're going to put the initial, which is 22. Now, we want to clean this up because it's very messy right now. So let's make this number here, these two numbers, into one. So we're going to multiply this out, put this on your calculator, and you're going to get 150.48. And if you multiply the units, you see that the grams is on the top, and over here the grams is on the bottom. So this will cross out. And we're going to be left with joules per Kelvin. And we still have to bring down the X minus 22. Now, two things we could do. Either you factor this number out and multiply it by x, and then also multiply it by 22, or you can divide this number on both sides, and that's what I'm going to do. Let's see, we get 150.48 joules per Kelvin. Put this on your calculator, and you're going to get 1200 divided by 150.48. You're going to get a number of 7.97. In terms of units, we see that the joules is here, and also another joules is here. And they cancel out. So we are now left with Kelvin. Now we set this equal to x minus 22 because this has crossed out already. And we're only left with this. In order to cancel this out, we need to add 22 on both sides. And then we get that x is equal to, so you do 7.97 plus 22, you get x is equal to 29.97. We're going to round that to 30 degrees Celsius. Now, in terms of units, you may see that I have Kelvin here, but my answer, I'm going to leave it in degrees Celsius. The reason that I don't need to worry about changing the 22 degrees Celsius over here to Kelvin, even though I use a specific heat capacity that has Kelvin instead of degrees Celsius. The reason I don't have to worry about changing this unit is because delta T is the difference of two temperatures. So let's say I would change the number 22 to, let's say, Kelvin, which would be add 273. And I would also change 30 degrees Celsius also to Kelvin, which would be add 273. If you take the difference of those two brand new numbers, you are still going to have the same delta T. Let's think about it. If you add if you're going to change two numbers by the same number, you're going to add 273 to both of them, and then you're going to take the difference of both of them, you're still going to get the same difference. So that's why it's not necessary to change the temperature here, because it's delta T and you're getting the difference between two numbers. Even if you change the unit from degrees Celsius to Kelvin, you're still going to get the same difference. So it's not necessary. All right, so for this question, we got x is equal to 30 degrees. Let's move on to the next one. How much energy is required to vaporize 10 grams of water at its boiling point? Okay, once again, we got to know, is this talking about change in temperature? No temperature is mentioned here, so I know that it can't be the first equation. The key word here I see is vaporize, and that's telling me that I need to use the heat of vaporization equation. So I'm going to write it down. Q equals mHV. And they tell me that I am calculating energy. So I'm calculating heat. So Q is my X. And now they tell me that there's 10 grams of water. And they tell me that we're talking about water, which is important because, once again, they don't give me the heat of vaporization constant. They tell me it's water, so they expect me to go to table B and find that constant. So it is 2,260 joules per gram. I multiply these numbers out, I should be getting Q is equal to 2260 joules. So I got 22,600 joules. But once again, what if the question asks me to calculate the heat but in kilojoules, not joules? What would I do then? So what would the heat be in kilojoules? Well, two things you can do. Either the joules, you move the decimal 3 spaces to the left, or divide it by 1,000. So if you divide this by 1,000 or move, since there's no decimal here, you're going to start at the end of the number and go 3 spaces to the left and then stop. So that tells us that in kilojoules, this would be 22.60